Okay, so I'm going to talk in this video about the non-zero initial displacement and velocity. So we are going to have non-zero initial displacement and velocity in our case here. Okay, let's go directly and see how we can understand this. Suppose the string has an initial displacement f of x, okay, and an initial velocity that is going to be g of x. So we have like initial displacement f of x and initial velocity g of x. We are going to write the solution y of f, x and t for the problem with initial displacement f and zero initial velocity. Okay, number one, this is one part of the solution. And the solution yg of x and t for the problem with zero initial displacement and initial velocity g of x. This is why we call it y of g. Then the solution of the current problem, is going to be, this is the general solution, okay, is going to be the solution of, or the superposition of the two solutions, which is one related to y of f, means that the problem with initial displacement f and zero initial velocity, and here this is the solution which is yg of x and t, which is the problem with the zero displacement and initial velocity g of x. That's it. This is how we can deal with the issue where that we have non-zero initial displacement and velocity. Okay. This function satisfies the wave equation and boundary conditions because both yf of x and t and yg x of t, x and t do. As you can see here, for example, y of x and 0, which means that at t equal to 0, what is going to happen? This function, it is going to be yf. This is the problem with initial displacement of f and 0 initial velocity, right? Plus yg of x and 0. How this value is how much here? Exactly, because it is, we said that as if the initial, in this case it is going to be 0 initial velocity, right? So it is going to be 0 here. So we are going to end up with f of x, which is right. It is going, our function is going to be f of x. And here it applies for the case of velocity. Partial y partial t of x at t equal to 0. It is going to be exactly partial y f partial t at the same point of time, which is t equal 0, and partial yg partial t x of z, x on 0. This is how much here? This is what? Exactly, this is going to be 0. This is the zero initial displacement case. So we're going to end up with g of x. Then our function is going to be g of x, which is right. Okay. Okay. Now let's go to an example to understand it clearly, and you are going to find it easy to be applied. We will solve the wave equation from 0 to L with y of 0 and t equal to y of L, capital L, uppercase L, and t equal to 0. Means what? At x equal to 0, the wave is going to be 0. The position is going to be 0. And at x equal to L, the wave also is going to be 0. As if that we have like boundary condition 0 and 0 at the end. Okay? Okay. And we are going to say that it is going to be subjected to initial position, which is with a function f of x equal to x fx between 0 and L over 2, or L minus x fx between L over 2 and L. And in the same time, it is going to be subjected to initial velocity g of x, where this g of x equal to x times 1 plus cosine pi x over L. Okay, so we have initial displacement, we have initial velocity. Okay, the solution y of x and t is the sum of the solutions of the problem solved in example 16.1 and 16.3. If you remember, this is the solution of 16.1 in the previous video, and this is in the previous video directly, 16.3. You're going to find them, and we explained how we obtained them. So this is going to be our wave equation in this case. Summation from n equal to 1 to infinity, 4 over n squared pi sine n pi over 2 sine nx cosine nt. Okay, this is going to be like the coefficient here in this case, and this is two functions giving us x and t, and the second part is going to be the same also. It is the same, 3 over 2 sine x sine t, and then we have some coefficient here. Do you remember this is for n equal to 1, this is for n equal to n equal to 2 until infinity. This fraction times sine nx sine n t, right? Okay. Now in the figure you are going to find that we are going to end up with the following figure. Sorry, let's clean here everything. Okay, it seems that's okay. So let's start here. Here this is going to be the case where that 0.2, the first one is going to be. So this is 0.2. This is going to be the next one. I'm not sure. They are having like 0.2, 0.6, 1.2, 1.8. So it is going to be like this. Here this is 0.2. This one is going to be 0.6. This one 1.2. The upper one is 1.8. And then we are going to have some partial part here. This is, I think it is 2.3, and this is going to be 2.9 if I'm not wrong. Okay, so remember that from 0.2 it goes up like this, and all of a sudden then it goes down after that, when starting from 2.3 and then 2.9 and so on. Okay, so remember this is how the wave it goes. So it will go like something like this, this, and then like this, and then like this. Okay, this is how the wave is going to be described, and this is how this equation actually is providing us. This equation is providing this shape, okay, this complex shape, and still we are at 0 here and at pi here. As you can see, they are what? Exactly 0. It is 0 here and 0 here, right? So we are right in the boundary condition. We said that in the beginning, right? This is the boundary condition that we have mentioned in the beginning. Y of 0 and t equal to y of L and t equal to 0, right? So it is 0 at the beginning and at the end. Okay, thank you, and see you in the next video.